Hello. So today let's talk about the supremum and infimum of a partially ordered set. Okay, so this is a episode based on our discussion from last time, right? So we discussed the definition on a partially ordered set, and we also saw some properties, right? So that has to be satisfied in partial order set. Okay, so to begin with, let's first define a partial order set. So suppose, okay, let's have this set X, okay, and we're gonna have this binary relation R, okay. So this is a partial order set. Okay, good. All right, so then we're gonna try to define the supremum and infimum of this partial order set, but actually we're gonna do that on a subset of this X. Okay, so let's consider a subset, some S, okay, of this X. Okay, so before the defining the supremum and infimum, okay, we need to have some analysis on this, on those extreme values. Okay, so this is kind of sort of different from the common extreme values that we see in the totally or fully ordered set, right? So, okay, so first we're going to define a so-called maximal, and minimal. Okay, so we say that a maximal. So this is sort of like a local optimal, right? That's why it's called maximal and minimal. Okay. So because in the partial ordered set, we sometimes we cannot compare two elements, right? So that's why we use this kind of name. So a maximal element, okay, of this subset S is an element. Okay, let's have some, maybe using the X upper bar, okay, which is an element from of this S. Okay, and there's no any other X in S. Okay, such that we have this X, okay, partially ordered to this X upper bar. Okay, all right, and correspondingly we can define a minimal element. Okay, okay, so this partial ordered this binary relation R, it has direction, right? So normally when we write in this direction in R, then that means essentially you can imagine the previous example from last episode, right? So where we have this R2, then this can be regarded as the greater than or equal sign, right? So it has a direction. Okay, so a minimal element of S, okay, that is also an element. So let's call that X lower bar, right? And there's no such X such that so X, let's say like X lower bar, and it has a binary relation to X. Okay, good. So what do we mean by this sort of definition for the maximal and minimal? Okay, let's have a little picture. Okay, all right, and let's suppose we have this X to be R2. Okay, and we're gonna use the greater than or equal sign as our relation R, binary relation R. Okay, so this is the our partial order set. Okay, so this is the R. So don't confuse, don't get confused by those two, right? So this is the binary relation, and this is the Euclidean space R2. Okay. All right. So let's have this figure. Okay, let's say this is x1 and this is x2. Okay. All right. So let's say we have sort of a triangle. Okay. And we also have some. Okay, let's say we have this sort of triangle. Okay? And you're going to have this S. Okay, this is a subset of R2. So we want to we want to find this maximal and minimal. Okay, so you can see that this there is a maximal, right? We can directly see from this picture is this point, right? So this is the maximal of this S, right? So essentially, let's verify this definition. So this point, right? So we can call this maybe x bar, x upper bar. So that is the element S. That's true, and there's no any other x such that other x is greater than or equal to this x upper bar, right? Because this point is already we can essentially compare any other point, right? Actually, in this S to this point, and you can see that this point is it has a positive direction, right? So it has this binary relation. So if we call this x upper bar, so we can write any other point with this binary relation, right? In this S. Okay, so that's good. So we have found this maximal. Okay, but it's really difficult for us to find only one minimal element of S, right? So this is because, we have mentioned this before. So we can see that all of those points on this edge, right? So let's use a thick pen. We can see that all of those points on this edge, those are all the elements which are minimal of S, right? And as we mentioned from last time, we cannot, for example, we cannot compare those 2 points, right? Because each of those 2 points, each of those dimensions is greater than the other one, and in the other way around, right? So we cannot actually compare those 2 points. But so we can see that, but we can verify that all of those points on this this edge of this triangle, it's those points are all the elements with this satisfying this minimal definition, right? Because this is you can see that this is the point, right? So the minimal element of S on this, so that would be an element for this x lower bar, right? So for example, we call this S x lower bar. So that's an element of S, right? And there's no other point that we can say something about x we can write this x with binary relation, and then the other some other point, right? We cannot find any other. So even though let's try to make this point, we still cannot say something about this, right? Because we cannot compare. And if we want to use other points, maybe this, we cannot say that either, right? Because that would be the other way around. Good. So and then we have found all of those points on this edge. which are all satisfying this definition for the minimal element. Okay, good. So this is something that that'll be pretty useful for us to find something else. Okay, shortly. So, but let's say if you want to have only one minimal, you can have something like this, right? If we have a rectangular shape like this, and then you could find the only one minimal of S, right? Okay, good. So that'll be another example. All right. So before we can really define the supremum and infimum, right? So what do we need else? So you have already known that we must need the definition for the upper bound and lower bound, right? And actually, we will also need to find the greatest and the least element of S based on the upper bound and lower bound. Okay, so before that, let's define the upper bound and lower bound. Okay, good. So let's say little x. Okay, we call this upper bound. Okay, if okay, for say if for all y, which is also a point in S, okay, we're gonna always have this binary relation x then this y. Okay, so we can read this as maybe greater than or equal, right? So x is bigger than y. We can read it easier like this. So and correspondingly, we can say that x is a lower bound of S if for all y. So that would be the other way around, right? So y is bigger than x in partial order. Okay, so all right. So now let's have a look and let's try to find this little upper bound, this upper bound and the lower bound on the picture. Okay. So this is the minimal. Okay. So where's the set of the upper bound for this set S? Okay, and those points. Okay, the set of this upper bound, it has to satisfy this condition, right? So we're gonna always have those elements in this upper bound set, and we're gonna have those x. They're always bigger than those points in S. Okay, so in this R2, we have to find something. Okay, for example, we have to let all those two dimensions are greater than or equal to those points, right? So that'll be, let's use this solid line. Okay, so that'll be exactly the points to the right and above of those two lines, right? So we're gonna have all those as this would be the upper bound. So the set of upper bound of S, right? Okay, and for how about for the lower bound? So the set of lower bound, that would be, we need to first find this point, right? And then from below to the below and to the left, and of this point, we're going to have this as the set of the lower bound, right? So this would be the set of lower bound of S. Okay. All right. Good. So, and then we have found those two sets, okay, for the upper bound and lower bound of S. All right, so we're gonna define something, okay, based on the upper bound and lower bound, okay, and which would be helpful for us to define the supremum and infimum, okay. So we say that, okay, so if some x, so it has to be in S first, so it is an upper bound of S. Okay, so remember that here, right? So when we say that this is an upper bound, okay, so we don't know that whether this x is inside of S or not. We simply compared all of those with the points in S, right? And we say that x is always bigger than y, bigger than those points in S. But here we're saying something further. So we do not only have this x as an upper bound of S, but we also have this x is inside of S. So xx is the element of S. So that means, okay, so let's finish this first. Then we say that this x is the greatest element of S. Okay, so where is that point? Right, so that would be okay, so let's finish the other part, okay? Then we can show this on the picture. And let's say if x is a lower bound, okay, is the lower bound of S, then this x is we call this as the least element of S, okay? All right, so based on this, we're gonna say that if, okay, if the set of the upper bound of S has a least element, okay, then it is called a supremum of the S. Okay, so which is written as the sup x of S. Okay. All right. So that x is this x. Okay. So let's see. So if this x is a lower bound, let's say we're using this, right? If x is an upper bound of S, then x is the greatest element of S. And if the set of upper bound of S has a least element, right? As we said here, has some least element, and then it is called a supremum of S. Okay, but that point, this supremum point of S, but that point has to be the least of the set of the upper bound set, right? And that is written as the sup of x of S. Okay, so basically it means that, okay, for any point y in S, okay, we're not gonna have this sup xs we're gonna have this boundary relation between this and y. Okay, so we're gonna always have this supremum of this xs, so that is bigger than this y for all those points in S. Okay, and second, I'm gonna say for any y prime in X such that have this y prime bigger than y for all the y in S. Okay. Then we're gonna have this y prime that is bigger than the sup x xs. Okay. And that has to be the least in the upper bound, right? Okay, good. So basically, this is saying that we're gonna have the biggest one in S, but we're gonna have the smallest, the least one in the upper bound set, right? So what does it mean? And that is exactly this point, right? So this would be again, this is exactly the point of the sup of xs, right? Okay, so and later we're gonna define the infimum, okay, and we know that, or we can already know that this would be the point, right? So this would be the inf of xs. Okay, so now let's finish the definition for this first. Okay, so all right, so let's say if the set of lower bound of S, it has a greatest or the biggest element, then it is called an infimum of S, okay, which is written as inf of xs, okay? And correspondingly, we have those two conditions, okay, for any y in this S itself, we're gonna have y is bigger than the inf of xs, okay? So it means that this inf, that has to be the smallest point in S. Okay, and second, for the lower bound set, and that inf, that has to be the biggest one, okay? So for any y prime in X, such that we have y bigger than y prime for all y. So we can see that no matter we're talking about the set S itself, or the upper bound set, or the lower bound set, we can always use this partial order R, right? Because we're working on this partial this partial order set R2, right? And those are just subsets of R2. Okay, so for all y in S, and this inf of xs, that is bigger than y prime. Okay, and then we have already indicated this point as the inf of xs. Okay, good. So, all right, then we have found those supremum and infimum of those of the set S, right? So, and you can see that here we have this super of x as the same as the maximal of S, right? Maximum element of S. But because we don't have one specific minimal element of S, right? We have this triangle here and we have that edge. So, and there is no least element of S, right? But we have this infimum of S. Okay, so those are sort of different things defined, and we have to be careful of the things that we're gonna use. Okay, so that'll be everything for this episode. Good.